Hello students, and welcome back to the quarantine lecture. This is 2.4. So in the last lecture we had a little fun. We played with the tensile test apparatus and we looked at that. What we're going to do today is we're going to put that in context of actual engineering. All right, guys, so before we get into it, just a quick reminder of what we did last time, right? So this is just a picture of our tensile test apparatus. Remember, we put our dog bone material sample into our tester. We applied a sample, and eventually what happened was that got longer, and longer. And what we would do in a normal tensile test, we didn't actually do any of the measurements, but what we'll do in a normal tensile test is you'll hook it up to a load cell, you'll know how much force you applied, and you'll be able to measure the elongation of that sample. So what this ultimately does is it gives us a form of what's called stress strain testing. So what do we mean by that? The stress on a material is the applied force divided by the cross-sectional area of the sample. Now that may sound very familiar in terms of units, and it should, because it is essentially a pressure, right? Remember, pressure is a force per unit area, or force per area, and that's what this is as well, is it's the load that we're putting onto the sample by the cross-sectional area of that sample, right? So again, let's put that into context of our dog bone shape, right? If we're applying the same force to this entire material, right, we know that it breaks in here because there's just less material, right? And let's think about that. If we put the same force here throughout this entire thing, this right here has a larger cross-sectional area than this does. Therefore, the stress that is experienced by the material here is higher because it has less cross-sectional area. Remember, in that case, you have a lower denominator. It will be a higher value. Okay, so what you're seeing here is the equation, which is force per area. And I do want to point out that it's A sub 0. The reason we use A sub 0 is because that is the initial cross-sectional area of the sample. Remember, as we were doing this, what happened to our dog bone? It started to stretch, it got longer, which means it was getting thinner. Instead of measuring that as we go, what we as engineers do is we make the call to just use the original amount, the original thickness of the material, okay? So that is A0, that's the original cross-section. And do note that engineering stress is expressed in units of pascals, which of course, as we know, is a pressure unit. The strain on the material is the dimension per unit length, is the dimension change, right? How much longer did our dog bone get, right? How much did it deform? Strain is similar to what we did before. It's normalized to what we call engineering strain, which is over, again, the initial length, right? So it's change in length divided by the initial length. So delta L over L sub 0, where the epsilon there is engineering strain, L is, of course, the various lengths, and then L sub 0 is the initial. So what this is really just saying is what's the change divided by what the initial was, right? Rather straightforward, okay? Do note that we are not taking into account any changes in the diameter. Again, we're not looking at how much thinner it gets. We're only looking at the ultimate length of the material. So what we can generate out of this is a stress strain curve. Now, I do want to point out one key concept here. Stress versus strain. Okay, we are applying a force to this that makes something happen, which means that the application of a stress causes a strain, right? It makes sense. The application of our force causes the deformation. Stress causes strain. Strain does not cause a stress, right? The basic relationship between these two describes the properties of material. And what we do is we lay this out in what's called a stress strain curve. And that's what you see. Here's a stress strain curve. On the bottom, we have the strain. On the x-axis, we have the strain. On the y-axis, we have the stress. Okay, now there's a lot of things to take away from this curve as we look at it. The first area you have is the elastic region. Okay, the elastic region is down in that straight area. We then have the yield point, which is that little dot you see there, and that's where it's no longer straight, and we start to see the curve actually become a curve. The maximum stress a material can handle under tension is the ultimate yield stress, and that's at the very top of the curve. You see it there on the y-axis. The final recorded point on the stress strain curve, way over here, This is noted by a black X on the curve, and that's where the material breaks. And the fracture stress is the stress at which the material breaks, right? So you just draw that line over. So the elastic region, like we talked about, the reason this is straight is because this does correlate, of course, to our elasticity, right? This is the region of our material where any force within that amount applied, the material will go back to its original shape. It's only after we hit the yield point and we move into the plastic region, which is the top part of the curve. This is where the material is permanently deformed, right? So again, let's go back. The elastic region, this is non-permanent deformation, right? This would be the stretching of a material, but it would go back, right? All materials will have this to some extent. Obviously, some materials will be able to handle it a lot more than others, but all materials will have some range of elastic where it can experience some sort of stress and go back to where it was before. But once we get into plastic deformation, that is where our material has actually started to change shape, right? And I want to fundamentally ask you the question, right? Why does it go up and then come back down, right? Think about that. Why does it start doing that? Well, we've seen that before in our materials where they actually start, right? We looked at our silly putty where we were hanging it, and all of a sudden it started to actually rip itself apart under its own weight, right? That's where the material itself became so thin that it could no longer support its own weight. And that's what's happening here, is at some point we've stretched it so long, so far, it's become too thin in the middle and it just goes, right? It just falls apart, okay? Plastic deformation, like we talked about, if you follow this curve and then you suddenly stopped putting the load on, you could actually track the permanent deformation by drawing a straight line that follows the elastic unloading, as we show here, right? So what this is showing here is, let's say we take it up on a curve to a point that it's still not falling apart, but it's stretched a little. If we draw a line back down with elastic and then we look on the x-axis of where that would be, that will correspond to the plastic deformation of the material, how long that material would have stretched and not gone back to its original shape, right? We can actually track that with this plot curve on how much it would deform. What would our tolerances be? That's how we would use this as an engineer. What would our tolerance be for deformation? Can we tolerate any deformation? That's where we would use these curves to help figure this out. So, very simply, let's go to a sample problem on course handbook page 60. What you see on that page is a stress-strain curve for a material. What will happen to a material if it experiences a tensile stress of 75 megapascals, 175 megapascals, or 250 megapascals? All right, so hopefully you've had enough time to do your answer. So at 75 megapascals, what we're showing here, right, you just look at it on the y-axis and draw the line over it. 75 megapascals, we are well in the elastic deformation range. This means that nothing would have happened to the material. The material will go back to where it was. However, at 175 megapascals, we are well into the plastic deformation range. So if we were to apply 175 megapascals, it will start to deform. If we were to unload that, it will draw back down, but it will still maintain some of its length that it had stretched. And if we take it all the way to 250 megapascals, that corresponds well to fracture. The material would have fractured at that point. Okay, so we can use these curves to help us as engineers determine, can this material withstand the stress we need it to? Like, for example, in the example that we looked at, if we knew that a truck was going to drive across that and apply a force of 300 megapascals, we would know that that material was not suitable for application. So these stress-strain curves, which we developed through the testing that we talked about in the last lecture, can be very useful to helping us as engineers make our material selections. So that's why we do it. All right, so that's it for stress and strain. Join us back for the next lecture, which is deformation and fracture.